The key idea behind doing a theory-based test for the slope of linear regression is that under certain validity conditions, the distribution of slopes from the shuffled data will be approximately bell-shaped. So in our example of the association between GPA and number of hours spent on non-academic activities, our null distribution looked like this. So in this simulation, I got a simulation-based p-value of 0.031. In that case, we can use a t-distribution to compute the p-value. So for example, here we would find the area underneath a t-distribution to the left of our test statistic, the sample slope. And in this case, our theory-based p-value is 0.031, which happens to exactly match our simulation-based p-value. There are three validity conditions for a theory-based test of the slope of linear regression. The first is that the general pattern of the scatter plot should be linear. So for example, you would not want to use a theory-based test of linear regression when you saw a curve in the scatter plot. The second validity condition is that the dots should be approximately symmetric around the regression line. If you have outliers that don't fit the trend of the regression, as shown in the scatter plot here, then we can't necessarily trust the p-value we get from theory-based linear regression. And finally, there should be constant vertical spread around the regression line. So an example that does not have constant vertical spread might be a scatter plot that looks like this. This is a pretty common type of non-constant vertical spread known as a fan shape, where the regression line fits very closely to points that have low values of the x variable, and then our predictions become worse and worse as our explanatory variable becomes larger. To do a hypothesis test for linear regression on a TI-83 or TI-84 calculator, you start by pressing Stat and going to Edit and entering the data into lists L1 and L2 just the way we did to make a scatter plot. Then press Stat and go to Tests and choose linreg t-test. The line that says beta and rho is where you specify the direction of the alternative hypothesis. And you can just leave blank the line that asks for the regression equation. For large data sets, you probably don't want to type all the data into your calculator. So many homework problems will give you output from the correlation regression applet or from Minitab instead. In the regression correlation applet, you can get the theory-based p-value by clicking the box that asks for the regression table. Here's how to interpret this output. The column marked coefficients tells us the y-intercept and the slope, or coefficient, of our explanatory variable. So in this data set for GPA and hours spent on non-academic activities, our regression line is predicted GPA equals 3.5977 minus 0.0059 times the number of hours. The p-value that we're interested in is in the last column, marked p-value. Typically, you can just ignore the p-value on the first line, the line marked intercept. This is the p-value for a test of whether the y-intercept in the population is equal to or different from 0, which usually we're not that interested in. The p-value on the line for the explanatory variable, in this case hours, is the p-value for a two-sided alternative hypothesis. To get the p-value for a one-sided alternative hypothesis, start by checking that beta hat, the slope of the regression line for the sample, agrees with the direction of the alternative hypothesis. So in the example of GPA and non-academic hours, we were testing the alternative hypothesis that there was a negative association between people's GPA and how much time they spent on non-academic activities. In the regression table, we can see that the slope of hours is negative, so that agrees with our alternative hypothesis. Then we can divide the p-value by 2. So here, our p-value for our one-sided alternative hypothesis would be the p-value in the last column of the regression table, 0.0624, divided by 2, so 0.0312. As a side note, if the beta hat sample slope did not agree with the alternative hypothesis, then after dividing by 2, you would subtract the p-value from 1 to get the actual p-value for the alternative hypothesis that you're testing. So in this example, if we had been testing whether there was a positive association between GPA and hours spent on non-academic activities, then our p-value would be 1 minus 0.0312, so a p-value of 0.9688.